On this video, we'll be doing this exercise. This is N4 Electrotechnics. If you have this book, you are lucky because you will get a memorandum that is not quiet, a memorandum that speaks. But even if you don't have, don't worry, because this exercise is based on Ohm's law. So what we are trying to do here is we are trying to master Ohm's law and get to know the questions that they are likely to ask on Electrotechnics question 1. So on this exercise, as I have said, we'll be dealing with Ohm's law. So let us try to answer the questions here and see what we will learn. So on this exercise, on number 1, we are asked to calculate the potential difference across terminals of a cell. Okay, so we have a cell which has an EMF of 1,45. So let's draw this cell. Let me take this. So let's draw this cell. So we have a cell. It is underneath my file here. It's a pen. So we have a cell as we are told. So this cell has 1,45 volts, an internal resistance of 0,1. So we have internal resistance of 0,5 ohms when delivering a current of, okay, so we are not told what's connected, right? All we are told is that this cell has a current. It delivers a current of 0,5 amperes. So what we are asked to calculate is the potential difference. So let us write what we have. We have a current which is 0,5 amperes, and we have EMF of 1,45 volts. Let's use a different color. So if we want to calculate the potential difference, we would remember that we have the formula that says EMF is equal to PD, the potential difference, plus plus current times internal resistance. So if we want the potential difference, we would then say the EMF minus IR. I hope you get how I got this formula. If you don't get it, you're not supposed to be on N4. Then the EMF is 1,45. I'm joking. Then the current, we are told that it's 0,5. Then the internal resistance, we are told that it's 0,52. So let's just punch this on a calculator. This would be 1,45 minus 0,5 times 0,5. This gives us 1,2. What we're calculating is the potential difference, so it's in volts. So That's how we would calculate the potential difference for this cell. So this book also tells us what the answer should be. So we just got that answer. Let us continue and do number 2 on this exercise. So on number 2, we are told that a battery has an EMF. So we know that we have a battery again, which has an EMF and internal resistance. What else? We are told that it is connected across 2 coils in parallel. So we have a cell and we have 2 coils that are in parallel. Okay, let us draw what we are just told, or let's finish which has a resistance of 10 ohms and 15 ohms respectively. So what they are telling us here is that we have a battery. Let's draw that battery. And this battery has internal resistance. With me, it doesn't matter which side we draw the internal resistance. So this cell, they said the EMF is 8 volts, and they said the internal resistance is 0.8 ohms. They said this cell, this battery, is connected across 2 coils in parallel. So these are our coils. These 2 coils, they are said are connected in parallel. So that is, both of them are connected across this cell, these 2 coils. So they said the resistances for this coil are 10 ohms and 15 ohms. So we'd say this is R1 and this is R2. This is the statement that we got here. So what they want us to calculate, the potential difference across the battery. Okay, let's start by doing that. Let's draw a line. So now, if we want to calculate the potential difference, as we are told, what do we know? We know the EMF, we know the internal resistance, but we do not know the current because the statement didn't tell us the current. But since we know these 2 resistors that are in parallel, if we can get the total resistance of this parallel circuit and add it to this one, we can then calculate the total current of the circuit. After getting the total current of the circuit, we can then get PD through that formula. So let us do that. Let's calculate the total resistance of this parallel circuit. It's gonna be R1 times R2 divided by R1 plus R2, which is equal to 10 times 15 divided by 10 plus 15. So let's punch that on the calculator. 10 times 15 divided by 10 plus 15. This is equal to 6 ohms. So if we want the total resistance, we will then take this parallel circuit total resistance and add it to the internal resistance. This is 0, this is 6, sorry, plus 0.8. and this will give us 6,08 6,8 ohms. So now that we know the total resistance and we know the EMF as given there, we can calculate the total current. Let us calculate the total current. The total current will be given by the total voltage, which is the EMF of the battery, divided by the total resistance. So this would be 8 divided by 6,8, and this would give us the total current of, let's say, the 8 divided by 6,8, it is 1,176 amperes. So if we know the total current, we can now calculate the potential difference using that formula. So PD is equal to the EMF, which is 8 minus current 1,176 times the internal resistance, which is 0,8. So it's 8 minus 1,176 times 0,8. This is equal to 7,059 volts. That is it. So we got the potential difference for 2.1, and it's exactly what they wrote here. I don't know, maybe sometimes we'll get something that is different with what they wrote here, as long as we have followed the steps correctly. Now they say we must calculate the current through each coil. That means the current across this resistor and the current across this resistor. This is not hard because current, which is I1, current across R1, we will say this is current across R2, I2. So if we know the potential difference, we know that if this is a parallel circuit, then it's the same through every resistor. So we will just take the potential difference that we got and then divide it by R1, and then for I2 it will be the same thing. We will take the potential difference that we got and divide by R2. So let us calculate that. 0,059 divided by 10, then our I1 is 0,706 amperes. And now let us go and calculate I2. The 7,059 divided by 15, it's gonna be 0,471 amperes. So that's how we calculate the current through each coil or through each resistor, as they have said. Now let us continue. They said what else we must calculate. Let's check. Okay, we did got these values that are here. We got this one, we got this one. Now they are saying let's calculate the power absorbed by each coil. So if we know the current through each coil, we can calculate the power. Now let us calculate the power through each coil. Let's use this one. I hope you remember the formula that says P is equal to I squared R. So for P1, we're gonna take that current that we got and we will square it and we will multiply by 10. Then we'll get the power. For P2, we will take the current that we got, we will square it and we will multiply by 15. Then we'll get the power. So let us do that. 0.706 squared times 10. So the current for P1 would be 4,984 watts. And what would be the current for P2? It's gonna be 3,32. Then that 7 would change and be 8 watts. Let's see what they got here. Well, then theirs is a little different. No, it's the same because we can still round off to 3 here. And did we get that one? Yes, we got it here. So that would be it for number 2. Now let's go to number 3. Again, let's draw a line here. What is the statement on number 3 saying? A cell has a terminal. So again, we have a cell. Terminal voltage, EMF is 1,9. When supplying a load with a current of, so the total current, when the load is disconnected, the terminal voltage rises to, now this statement changes everything. When the load is disconnected, terminal voltage rises to. So now we need to differentiate here between this voltage. If they are saying a cell is connected, a cell has a terminal voltage of 1,9 V when supplying a load. This makes this PD and this makes this AMF. We will never have a potential difference voltage that is bigger than the EMF. So we know on the circuit that we have a current. We also know that we have a load that we are supplying. So they are saying we must calculate the internal resistance of the circuit. So now this is easy. Even if we wouldn't draw this circuit, but let's draw it. This circuit is like this. It has a cell. Since we are told to calculate the internal resistance, we know that we have it. We are supplying a load. So we know the internal resistance. No, we don't know it. Do we know the EMF? Yes, we know it. It's 203. And PD we know that PD is 1,9 volts across the load, and we know the current. They said the current is 8 amperes. So if they want us to calculate the internal resistance, they are not asking us something that we cannot calculate. From that formula, we can calculate the internal resistance. We will take PD to this side, and we will have IR equal to EMF minus PD. Now we want R, not IR. So R would be equal to EMF minus PD, all divided by I, and this is what is the value? Let's come and write here. What is the value for EMF? We said it's 2,03 minus 1,9, all divided by 8. So if we say 2,03 minus 1,9, we get this, and we divide that by 8. So what do we get? Our internal resistance is 0,0163 ohms. So that's how we can calculate the internal resistance. So did we get the value that is written here? Yes, we did get this value that is written here. Our internal resistance is like that exactly. Let us continue to another exercise. Now we are on number 4. On number 4, we are told that a battery, again we have a battery of 10 primary cells. This battery has 10 primary cells, has an open circuit EMF of 15. Okay, open circuit EMF of 15 volts. Let's draw this cell. This cell is like this, according to their statement. A battery has an open, okay, this is like, we have a battery. I'm trying to think. Then if they are saying it has an open circuit, so this is what we would do. I would draw it like this. So they are saying with 15 volts EMF, 15 volts. When a 30 ohm resistor is connected across the battery. Okay, now across this battery, let us complete the PD, the potential difference is 12. Okay, so this is PD. Okay, they are saying when they connect a 30 ohm resistor, that is the resistor 30 ohms, we get PD, the PD, which is 12 volts. So across this resistor we have a potential difference of 12 volts. I wonder what they're gonna say. We must calculate the current. Okay, what do we have? Let us write everything that we have. We have EMF, and our EMF is 15 volts. We have PD, 12 volts. Do we have an internal resistance that we are told of? The internal resistance per cell. We're gonna calculate it here, so we don't have it. The power. Okay. This is a series circuit, right? So if we have this potential difference and the resistance, we can use this to get the current. So the current that we are asked to calculate is equal to PD divided by the resistance. So if we call this R1, we'll say divided by R1, right? So this becomes 12 divided by 30. So what is it? 12 divided by 30. What is that? That is 0.4 amperes. So we know the current. On the second question, we are asked to calculate the internal resistance per cell. So again, we can calculate the internal resistance. You remember the formula that we made for an internal resistance? We said the internal resistance is equal to EMF minus PD all divided by I. So we just substitute here. EMF is 15 minus PD 12 divided by 0.4. Let's calculate that. 15 minus 12 is equal to 3 divided by 0.4. What is that? The internal resistance is gonna be 7.5 ohms. So you must remember something here. We know that the internal resistance must be small. So they told us something here. They told us this is a battery of 10 primary cells. So here we are asked to calculate the internal resistance per cell. So that means we will divide by 10 to get the internal resistance per cell. So we would say R per cell is equal to 7.5 divided by 10. So it's gonna be 0.75 ohms. So that's the internal resistance per cell, the power in the external circuit. So now we are asked to calculate power now. Which formula we're gonna use to calculate power? Our power can be calculated by PD over I. Why? Because they said we must calculate the power in the external circuit. So that is our external circuit. So let's substitute PD. We were given that PD is 12. We calculated I there. So our power would be 0.4 times 12, which becomes 4.8 watts. So the power is measured in watts. So we won. So we got this, we got that, and we got that. Let's go to number 5 now. What are they telling us here is that two cells are connected in series. Okay, two cells. Oh, do you see the difference between this, a battery and two cells? So there I made two cells, which was wrong. I was supposed to eliminate that and that, just join that there. Yes, I think this one was supposed to be big, eh? Yeah, and this one down here be small. That was a wrong drawing. Let's come to number 5. Two cells. Cell number 1 and cell number 2 connected in series. And a circuit is completed by means of two parallel coils. Okay. We have two parallel coils. Another coil. So let's put the values. Are we told that the coils are, yes, this one would be 7 ohms and this one would be 5 ohms. Are we told the EMF here? One cell has an EMF of, okay, that 1.5 volts and an internal resistance of 1.2 ohms. This one and the other cell 1.1 volts, 1.1 volts, and the internal resistance of 0.7 ohms. Calculate the current through the cell. Now we need the total current. Once they say calculate the total through the cell, not through R1 or R2, then we know that we must calculate the total current. Okay, let's write down everything that we have. What we have, we've got this EMF and this EMF. So if we want to know the total EMF, we must add this one and this one. Where will that help us? This will help us on calculating the total current of the circuit. So if we know the total EMF, we would then take the total resistance, calculate the total resistance of the circuit. After getting the total resistance of the circuit, we will then take the total resistance and divide it to the total EMF to get the total current. So total EMF is gonna be E1 plus E2. We know that E1 is 1,5 plus E2, which is 1,1. So this gives us 2,6 volts. The total resistance of the circuit will be calculated by calculating the total resistance across this parallel circuit. If we say this one is R1 and this one is R2, we'll then say R1 times R2 divided by R1 plus R2 plus these resistors, internal resistances are in series. So if we say this is R1, this is R2, so plus R1 and R2. So let's substitute. This is 7 times 5 divided by 7 plus 5 plus 1,2 plus 0,7. So the total resistance of the circuit tends to be Let's calculate that. 7 times 5 divided by 7 plus 5 plus 1 comma 2 plus 0 comma 0.07. What is that? Total resistance of the circuit is 4,817 ohms. So now let's calculate the total current of the circuit. Let's use a different color. The total current of the circuit, we said it's going to be ET divided by RT, which is the same as 2,6 divided by 4,817. So 2,6 divided by 4,817, this is equal to, so our IT is 0,53. Okay, this 7 changes this to 10, we carry 1 here, which changes 3 to 4 amperes. So is that what they got? Yes, it is. No. 5,4. Yes, it is. And now they are saying let's calculate the current in through each coil. So now we are calculating I1 and I2. So for us to calculate I1 and I2, we need to know the potential difference across this parallel circuit. So when we know the potential difference across this parallel circuit, we will use it to calculate the current across each resistor. So remember that formula can also be used to give us the potential difference. PD would be, let me use this color, EMF, which is ET minus IR. So we know that the current is 0,54, but now these are now, it must be substituted by the sum of these resistances. And what do we know is that the current through them is the same, since these cells are connected in series. That includes their internal resistances. So this R would be R1 plus R2. So we don't want to forget that. Current would multiply that sum. So it's, we said it's 2,6 minus 0,54 into 1,2 plus 0,7. Let us now calculate this. ET is 2,6 minus current 0,54 into 1,2 plus 0,7. Please write every step when you are writing your exams. So that is PD equal to that. So that is the voltage for PD. So now we can use this voltage to calculate a current across R1. So current across R1 would be, let's use this one. We will say a current here is I1 and the current there is I2. We will take that voltage and would divide it by 7. For I2, would take this voltage again, because that's a parallel circuit, and divide it by 5. So let's go. 1,574 divided by 7 is equal to 0,225 amperes. A current across I2 would be 1,574 divided by 5, and this would give us 0,314. Oh, let's round off here, amperes. So that is our I2, and that is our I1. What else we are asked to calculate here? It's the terminal voltage for each cell. Terminal voltage for each cell. So now they are asking us to calculate the terminal voltage of each cell. So terminal voltage for this cell and a terminal voltage for this cell. Now they want us to separate, like, remember when we calculated this volt drop, it was across this one. So they want us to calculate it across this one and across this one. So let's go. Let's calculate the potential difference across the first cell. So how are we going to calculate that? We will take 80 and we will minus by I, which the current is the same because these cells are in series, but now we will use R1. Remember, our ET now is not this one, because we are using only this cell, so we would say E1, not ET, for us not to confuse whoever will be marking our paper. So this would be 1,5 minus the current 0,54 times the internal resistance, which is 1,2. And for PD2, we would say E2 minus current, then R2. So we would take now 1,1 minus the current, because the current is the same on a series circuit, and we would multiply by 0,7. Let's now punch this in a calculator. It becomes 1,5 minus 0,54 times 1,2, and this is 0,852 volts. Let's come to this one. 1,1 minus 0,54 times 0,7. This is equal to 0,722 volts. So let's check if we are in line with the answers that they gave us. Yes, we are in line. So that's it. The only thing that is flipping is this one, but I think it's them, not us, because we just punched this in a calculator. If it's us, then you know where I have made this mistake that I don't see. Let us continue. We were here, right? Let us go to number 6. Number 6. On number 6, what are we being told? On number 6, we are told that we have a 20 ohm resistor. What is happening with this resistor? It's connected across a rheostat. Okay, 20 ohm resistor connected across a rheostat. Okay, so this is like, let's try it. This is like we've got this, and this is a 20 ohm resistor. This resistor is connected across a rheostat. So this is our rheostat. So 20 ohm resistor connected across the rheostat, which is then connected in series with the heater element of 600 ohms. What is then connected across a heater element? A rheostat and this resistor. They are then connected across. So it, with me, it doesn't matter whether you draw a line here or you draw a line here. These two are in parallel, but this one is said to be in series with these. So this is our element, heater element, which is 600 watts. What must the value of the rheostat be so that the heater draws a current? Or what must be the value of the rheostat be so that the heater draws 10A when the whole circuit is connected across a 100-volt supply? So we know that this is AC because that's what we use for heaters, and here we are not told of a battery or a cell. So we know that we have an AC source which will represent with that, and we have 100 volts AC that connects everything that we have. So our current, they said a heater draws this current, so that means since that it is in series with those, that means we have 10 amps current. This current is not the same with the current across there because the current will split there. Okay, now let us get what they want us to calculate. Value of the rheostat. By the way, we are not told this rheostat, the value of it, so they want us to calculate it. So if we say this is R1, a rheostat would be R2, and this would be R3 or RS, the resistor in series with R1 and the rheostat. So how can we calculate R2? What do we know here is the total voltage and the total current. Okay. Across here, we've got that unknown. What is the total resistance? The total resistance of this circuit is R series plus that R parallel. So if we would substitute here, if we would say RT, and if we would want to calculate that one through RT, we would have to say RT, R parallel plus R series. So can we get this and this? Rs, we're not told Rs, right? Yes, we're not told Rs. But though we're not told Rs, we can get Rs if we have a power here and we know the current across there. Let's calculate Rs, which is the unknown, through the formula that says P is equal to I squared over R. This formula can help us to get Rs, right? Yes, let's use the formula. We want R, so which is Rs. Now let's make Rs the subject of the formula. So we'll have P divided by I squared. So let's substitute. This is going to be 600 divided by 10 squared. 600 divided by 10 squared. This is equal to 6 ohms. So we know Rs, that is 6 ohms. Let's now see if we can get RT. We also know that R parallel is unknown, but we can get RT through the voltage and the current, right? So RT is V over I, since because V is equal to IR, right? Voltage is the product of current and resistance. So if we want R, we just divide V by I. So what is the voltage? 100 volts. And what is the current? 10. So the total resistance is 10 ohms. So another value is being known here. So we know RT and we know Rs. So we can get R parallel. How do we get R parallel? We can get R parallel by saying RT minus Rs. That's how we can get R parallel. RT is 10 minus 6. So R parallel is equal to 4 ohms. So after getting R parallel, where does R parallel helps us? Remember, R parallel is gonna be R1 times R2 divided by R1 plus R2. So if we would cross multiply, we would get R parallel being multiplied by R1 plus R2 equal to this is maths, R1 R2. So if we would cross multiply there, we would get R parallel R1 plus R parallel R2, R1 R2. So if we would substitute, if we would transpose this to this side, R parallel R1 is equal to R1 R2 minus R parallel R2. So we have a common factor, which is R2. So R2, and which is the rheostat, into R1 minus R parallel. So, okay, sorry, that was R parallel and R1. So what's happening now? We have R parallel R1, so we want R2, so we divide by R1 minus R2, divide by R1 minus R2, so these cancel. So R2 is equal to R parallel R1 minus R2. So we can use this formula to get that resistor, the rheostat, the value of the rheostat. What is R parallel? We said it's 4. And what is R1? We said R1 is 20. And what is R1? We said R1 is 20. And what is R2? How did we? This is R parallel. Sorry, R parallel and R parallel. R parallel. So what is R parallel? Is 4. Let us punch that in a calculator. 4 times 20 and 20 minus 4. This is equal to 5. So R2 is 5 ohms. Let's see if we are correct. 5 ohms. So if you want to, if this is confusing you, you can just substitute the values there and then solve it as you go. I just liked doing this and it worked for me. So now let's do where we were here. So let's go to number 7. We still have number 8. Ooh, this is gonna be long, but let's just finish this exercise. On number 7, this is what we are told. On number 7, they are saying 2 series circuits. So we have 2 circuits. But what do we know about these circuits? They are in series with branches of 6 ohms and 4 ohms and 10 ohms and 5 ohms respectively. Okay, this is what they are telling us here. This is 2 series circuits. The first series circuit is 6 and 4. 6 ohms, 4 ohms. The other series circuit is 10 ohms and 5 ohms. So what is happening on these 2 series circuits are connected in parallel across a battery. So they are connected in parallel across a battery. How many cells? Which has an EMF and the internal resistance. Okay. We are told that these are connected across a battery that is internal resistance. So our internal resistance is 0.25 ohms and the EMF is 25 volts. So what are we asked to calculate here? Calculate the potential difference across each of the external resistors. Sure. So what we are asked here is to calculate. If we are saying this is R1, then we are asked to calculate V1. If we are saying this is R2, we are asked to calculate V2. If we are saying this is R3, we should calculate V3. If we are saying this is R4, we are asked to calculate V4. Does this make sense? Yes, it does make sense, because if these resistors are in series, then we have a volt drop here, we have a volt drop here, and a volt drop there, and a volt drop here also. Though we know that V1 plus V2 must equal to V3 plus V4. Why? Because this is a parallel circuit. So a sum of the volt drop here and here must equal. Okay, where do we start on calculating V1 and V2, V3, V4? If we can calculate the total resistance of the circuit, where will that help us? It will help us on getting the total current. Getting the total current, where will that help us? Getting the total current can help us to determine the volt drop across here, or we say V parallel, or the potential difference of the circuit. Getting that potential difference of the circuit, where will it help us? That potential difference of the circuit will help us to calculate the volt drop across this one and this one and this one and this one. Okay, now we can start, because we know what we have and we know how it will help us on getting something that we want. So we said we'll calculate the total resistance of the circuit first. So we'll say here we've got RS1. RS1 will be R1 plus R2. And this is gonna be 6 plus 4, which is equal to 10 ohms. And we'll have RS2, which will be R3 plus R4. And this would be 10 plus 5, which is equal to 15 ohms. What do we have now? We've got a circuit like this, now, and this is 10 ohms and this is 15 ohms. So we can now calculate the total resistance of this parallel circuit, and it's going to be calculated by 10 times 15 all divided by 10 plus 15. Let's punch this in a calculator. 10 times 15 divided by divided by 10 plus 15. This is equal to 6 ohms. So now we know the total resistance of this parallel circuit. We need to add it to this internal resistance to get the total resistance of the circuit. So let's do that. RT is equal to 6 plus 0.25. Then the total resistance of the circuit is 6.25 ohms. So we said this will help us on calculating the total current of the circuit. So we then take 25 and divide by 6,25. So 25 divided by 6,25 is equal to 4, or 4 amperes. That's the total current of the circuit. We said this total current of the circuit will help us to calculate that volt drop across this circuit, which is across there. And this is gonna be the product of total resistance across the parallel circuit, resistance, and current. So it's gonna be R parallel times IT, which is 6 times 4, and this tends to be 4 times 6 is 24 volts. So how can we get V1 if we know this voltage? V1 can be calculated by using these two resistors. So you just take this formula and install it in your head, because there is no way you will get it if we are using this textbook that I'm using. So we will say R1 divided by RS1, which is that one and this one, times the volt drop, which is the volt drop across the parallel. So this will give us V1. It's the same with V3. We would say R3 divided by RS2. So you take this resistor, you divide it by the sum. You take this, you divide it by the sum. So you multiply by V parallel. So let us substitute there. Let's use a different color for this. R1 is 6 and RS1 is 10. V parallel is 24. So this gives us 6 divided by 10 times 24. What is the answer? It's 14,4 volts. So for us to get V2, we just take V parallel minus V1. So this becomes 24 minus 14,4, which is equal to, we'll ignore the sign, 9,6 volts. Let's come here. R3 is 10 divided by RS2, which is 15, divided by 15 times 24. So what do we get here? 10 divided by 15 times 24. We get 16 volts. So if we want V4, we would then say V parallel minus V3. And this is equal to 24 minus 16. We will ignore the sign again. This is equal to 8 volts. And this is exactly what they got here. 8, 16, 9,6 and 14,4. So let's jump into the last question. To the last. So we'll be done with this exercise, and we will be not afraid of Ohm's law wherever we go with electrotechnics. So let us consider this question. On this question, this is what we are told. A circuit consisting of 3 resistors, and we give them the values, connected in parallel. So let's draw that. 3 resistors connected in parallel. These resistors are connected in parallel, and the first one is 12 ohms, the second one is 18 ohms, the third one is 36 ohms. What is happening to these resistors? This combination is connected in series with the fourth resistor. I wonder what is the fourth resistor. So even if you take it here or here or here, it really doesn't matter, as long as you admit that this resistor is in series, R series. What is the value of this resistor? The whole circuit is supplied at 60 volts, and it is found that the power dissipated in 12 volts resistor is 36 watts. So we have 36 watts power across this one. Determine the value of the fourth resistor and the total power dissipated. Okay, the whole circuit is supplied at 60 volts. So again here, we don't know whether it's AC or DC, but it doesn't matter. So though we're not told, let's just use DC, because that doesn't change values. We are told that we have 60 volts there. Are we told of the internal resistance? No. They say we must calculate this resistor, because it's this one. They said it's R4. So this would be R1, R2, R3. What is that resistor? Okay, from here we can calculate R parallel. Where will R parallel help us? R parallel will help us. Okay, from here we are told of the power. So that means here we can calculate I1, but where will I1 help us? I1 will just help us on knowing I1. Okay, if we know the total voltage, what can this help us? Where can this help us? It's really hard to know where will that one help us. Okay, let's come here. If we know power, we can get this current. But from this power, are we getting the current only? No, we can also get the voltage across R1, which is V1. And we know that this voltage is the same here and it's the same there. Once we know the voltage here, we can get I2 through this voltage and this resistor, as well as I3. Wow. Once we know I1, I2, I3, we can get IT by adding these currents. So we would know the current that is across this resistor, which is the IS, and the IS is the same as IT. So once we know this current, we will need the volt drop across this resistor, and we can get it through this one and this one. Then we would get that R4. Now let's go and calculate that. What we must calculate the photoresistor and the power dissipated in the group. So the power dissipated on the group, by that they including, or they are asking us to calculate the total power. So the total power will be calculated by the total current and the total voltage. So let's first calculate this proof. So we said through what we have here, we can calculate I1, but we are not in a hurry to get I1, we are in a hurry to get V1. So we remember that we have a formula that uses the resistance and voltage. So this formula says P is equal to V squared R. So we want V, not V squared. So let's make V the subject of the formula. V squared is equal to P divided by R. But now let's square both sides for us to get V. So we need to substitute these values. We are told that power is 36 and the resistance is 12. So V is equal to, let's put that in a root, and on that root let's do that. That is 36 divided by 12. This is equal to 1,73 volts. So we know the voltage here and here and here now. So we can use this voltage to calculate I1 and I2, then we'll get I total. Okay, so I1 is equal to V1 divided by R1, I2, V1 divided by R2, I3, V1 divided by R3. Let's substitute 1,73 divided by 12, 1,73 divided by 18, 1,73 divided by 36. Let me use the different color here. So 1,73 divided by 12 is 0,144 amperes. 1,73 divided by 18, 0,096 amperes. 1, didn't we do anything wrong here? Was I right here? Let me double check. Let's continue here first. I'll double check that. 73 divided, I'm just seeing these values, they small. Okay, divided by 36. 36. We'll check this. We'll double check I1. Remember I1, we can get it through the formula of power. It's 0,048 amperes. So let us come back here. Let us come back here. 36 divided by 12. Oh, yes, I can see where my mistake was. It was with this formula. This formula doesn't say, I remember this formula. This formula, let's double check it here. Forgive me for my mistake, which is gonna make this video long. The formula says P V squared over R. Yes, yes. V squared over R. So that makes V squared be equal to P R. So if we square both sides, we get V equal to PR. So if we substitute there, it's 36 times 12. The root of 36 times 12 is 20,785 volts. So this changes everything here to be 20,785, 20,785, 20,785. I'm sorry about this mistake. So 20,785 divided by 12 is equal to 1,732 amperes, and 20,785 divided by 18. This is 1,155 amperes, and 20,785 divided by 36. This is 0,577 amperes. So this is what we get, and if we want I total, we will add this current. So let's add these currents. I said I1, we can get I1 through the formula of power, but let's just not do that. Let's just take that I1 that we got. I hope you remember that power is also equal to I squared R. So if you want I squared for I1, you would then say P divided by R, you square, then you get I1 from substituting power, which is 36 divided by 12, and it's what I did there. It's 1,73 amperes, and that's what we got for I1. So that is the other formula that you can use for I1. So IT is 1,732 plus 1,155 plus 0,577, which is equal to 3,464. Why we calculating IT? It's because we want to use this IT to get that resistor, because the total current flows through that resistor. So we know that to get R4 we will need V across V, let's say V4, which is V across V4 divided by I total. Now, how do we get V4? V4 will be 60 minus V parallel, which is V1, that one, 20,785, all divided by I total, which is 3,464. Then this becomes what? 60 minus 20,785 divided by 3,464 is equal to, then R4 is 11,321 ohms. So we did got R4 and we're asked to calculate the total power. Let's use this one for the total power. It's gonna be V times IT. So which V are we using actually? Since it's a total power, it's gonna be that V. 60 times 3,464. 60 times 3,464. This is equal to 20, 207,84 watts. That's the total power. Let's see if what we got corresponds with what they got. Sometimes having answers on textbooks is a problem, because when you don't get what is written here, you wanna die. We got this, it's here. Then we got this. Where is our R4? It's here. So we are right